Hey guys, we've very recently wrapped up our chapter involving integrals that require double integrals and triple integrals, so integrating over 2 and 3 dimensional regions. Now, in the spirit of Calculus 3, being a class that lets us investigate how to integrate not just with a single variable, we need to move on to what I'm going to call vector fields here. Okay, so we're kind of going to change gears. We'll get back to integrals soon, but what I'm going to do today is introduce a new kind of function that we're going to work with and ultimately integrate over. So let's go ahead and get started. First off, since it's been a little bit since we've worked with them, recall what vectors are in the first place. These are quantities unlike scalars that, unlike scalars that indicate both magnitude and direction. So examples that we played with before, things like velocity or things like force, you can, talk about the magnitude of each of those things, and you can talk about the direction in which those things point. Now, a question that we can pose, keeping this in mind, is what if we want to describe quantities like that at multiple locations simultaneously? Now, an example or a collection of examples that I could maybe give you guys are things like, if I could get my pen working here, things like force fields. If I have something like a magnetic field or an electrical field, or a gravitational field, situations like that, you have these forces being exerted basically everywhere to some degree or other, in different directions, in different intensities, and maybe you might want to specify what's going on in that kind of a situation. Another case where we might want to describe multiple vectors existing simultaneously, maybe things like velocity in a fluid flow is one. Lots and lots of money spent, investigating things like how airfoils work, how to make cars more aerodynamically efficient. We're investigating the speeds of air particles whenever you study those objects in wind tunnels. Or alternatively, you could be talking about like a liquid fluid. What's going on with things like, ocean currents is another example of velocity in a fluid flow. Wind is another, if I could spell here, wind speeds in different directions. This is another example of velocity in a fluid flow because air is a fluid. There's lots of examples of this. So how do I express these things? Well, this is where we're using an object called a vector field. If I want to clarify what that is, we'll go to the following definition. Let's go ahead and let D be a subset of Rn. Vector field on Rn is simply a function. It's a function f that takes each point in D to an n-dimensional vector. Now, if not obvious, D is chosen here to represent the word domain. We're expecting that this is going to be the input of whatever the heck this function capital F is over here, right? So we've got some sort of function that takes an n-dimensional point to an n-dimensional vector. And we can see this demonstrated in these two cases down here. Suppose that I've got either my 2-dimensional case or down here my 3-dimensional case. And this is a function, this first one, that takes a 2-dimensional point to a 2-dimensional vector. You'll notice there's only one comma here within the big vector as a whole. Similar deal down here. We've got a 3-dimensional point being taken to a 3-dimensional vector. And you'll notice we can kind of break this down a lot depending on what we want to focus on. If I'm looking at how this 2-dimensional point goes to this 2-dimensional vector, well, there's a scalar function telling me what happens in my x component, and there's also a scalar function telling me what happens in my y component. If I wanted to look at the 3D example, we have 3 such functions telling us what happens in each of those components. So really what a vector field is we're stacking together a bunch of scalar functions to build one big vector function, to kind of demonstrate what's happening with each of my components. Now, question from this, that's all well and good. What's the deal with the notation? What do these things look like? Well, let's focus on that for a hot second here. Notation. One thing that you will note is that when I wrote this function down on that last slide, that capital F had a big hat on it. Handwriting. Okay? Handwriting, what you want to do is use an arrow hat, kind of like we do for vectors, on your function to denote it's a vector field. Right? Use an arrow hat on your function to denote that it's a vector field. We don't necessarily have to use a capital letter like we did on that previous slide. If you wanted to use a little f with a hat on it, I guess technically you could get away with it. The key thing that you want to use here is just, kind of like I wrote it before, use a hat on it to denote that it's a vector field. Now, on the other hand, the reason that we do this in handwriting is because we can't use the book convention. Well, if I could spell here, my book convention. This is going to be something that's written in bold-faced text, right? So here, I guess I'll replicate this as best as I can. Your book is going to write something like this in bold font. That's kind of time consuming for me to do handwriting wise, as you just saw. So we'll go with the arrow convention for handwriting. You'll notice this is kind of the same thing that the book does when they're talking about vectors, right? If I was talking about a vector A or B or U or V or whatever, in the text, they boldface things to denote vectors, and we write things with hats to denote vectors, for not typing stuff out. So, of course, if this function spits out vector output, we want to differentiate this from a scalar function, which spits out scalar output, in the same manner, right? Treat your functions kind of like you would treat, a vector. If it's a scalar, we don't do anything fancy. If it's a vector, or if it spits out a vector, put a hat on it or make it bold-faced. As far as visualizing these things, we typically represent these by picking some sort of sample of points from our domain space. And what do we do with these? Well, we draw a collection of arrows at each of our points. Okay, to show the output there. So, for example, if the point 1, 2 is in your domain, well, what happens when you take 1, 2 and you plug it into your function? You get a vector. To draw this at the point 1, 2, emanating from that point 1, 2, draw whatever vector it was that your function spat out. Okay, so as an example here, I'll go ahead and try this with an actual vector field. All right, let's see if we can sketch this vector field, f of xy, f with a little hat on it, equals negative a half yi plus a half xj. Now, if you don't remember what those components were really telling me is, we're splitting up my vector field, into its component functions. This first piece is going to tell me what's going on in my x component, so that's really minus a half y. And this is going to tell me what's going to happen in my y component, that is 1 half x. Okay, so this is just an alternate way for me to view what's going on with f. Now if I want to track what this thing looks like, again, what we were saying on the last slide is, let's see if we can set up a table of points. corresponding vector output. So I'll just pick a couple sample points here. We'll start with the point on this side, and then I will figure out what vector it spits out over here. For example, I'll just pick a random smattering. Let's say I try something like, I don't know, 1, 0, 0, 1. We'll go with the negative 1, 0. I don't know, 0, negative 1. I'll just try a couple of these random ones here. If I want to figure out what these guys map to, I just plug these points into my function, right? So if I plug in my 1 and my 0 for x and y in my function, well, plugging in 1 for x is going to give me a half over here. Plugging in 0 for y gives me a 0. And I can repeat this process for every single one of these points. Okay, I'll go ahead and give myself some slots here. For this particular function, I am plugging in 0 for x, and I am plugging in 1 for y. It'll give me minus a half. For this next point, I'm plugging in minus 1 for x, so I'll get a minus a half here. And I'm plugging in 0 for y. It'll give me a 0 here. For this last point, which I'll close the parentheses on, I'm plugging in 0 for x, and I'm plugging in negative 1 for y. That'll cancel with the negative that's already there in my function, and I will get 1/2. So, what I am saying that we do to draw this is you start your vector at this point, and you draw it in this direction. So for this very, very first one, I am starting at the point 1, 0. You'll notice that from this point, I have to draw the vector which goes 0 units in the x direction and up a half unit in the y direction. So that looks like this guy, about so, right there. Let me put a better hat on that. It only goes up half a unit, and then it stops. Okay, similar deal for this next point. At the starting point 0, 1, which is right here on the y-axis, I need to draw a vector that goes negative 1/2 units in the x direction and no units in the y direction. So here's my negative a half unit in the x direction. I'll put a little arrow there to denote that's my vector. And similar deal for the last 3 points. At minus 1, 0, I need a vector that goes 0 units in the x direction but negative a half units in the y. And at the point 0, negative 1, down here, I need a vector which goes a half unit in the x direction and 0 units in the y. Now, you may notice, but we've kind of got this vector field that's giving me this somewhat swirling motion around the origin in R2. If we wanted more information, I'll go ahead and, note, for more info, basically try more sample points if you want to fill in what's going on here. If you wanted to draw in a couple extras here, you might get this guy. So I took a look at this a little bit earlier. This swirling pattern is emphasized if you continue drawing this with other points here. And we also do get a couple spots that pop up on the diagonal of this function. So this is mostly just for me looking at this independently, trying a couple of other extra points and, building up my table so I could plot more of these, right? If I want a really detailed vector function, throw more points at it, build a bigger table, you can add more arrows. Or, and this is kind of the cheater way to think about this, you can do a similar process in 3 dimensions. We can sketch in 3D, but for 3-dimensional vector fields and also for more complicated 2-dimensional vector fields, it's heck, for most vector fields in general, it's easier to have a computer do it, right? They'll throw tons and tons of arrows at you basically immediately. But at any rate, I'll give you guys an example of this. relatively easy one to do by hand. That's a three-dimensional vector field. This is a constant vector field. What this basically says is no matter what x, y, z you shove into this, you'll notice there are no x, y's, or z's over here, so pretty much any input is going to generate 1, 2, 3 output. So what that's saying is if we tried to set up a table, you know, the entire right-hand side of that table, if we'd set this up like the last example, it'd be populated by just nothing but 1, 2, 3's. Any point you want to start from, draw a 1, 2, 3 vector emanating from it. So, you know, I can try that. You know, if I've got this 1, 2, 3 reference box that I can build. Okay, so I'll do this in a slightly different color. Just so I can build a reference point here. We've got that if I wanted the 1, 2, 3 point, I had y'all draw reference boxes to sketch these kinds of things way back in the beginning of the semester. This is the 1, 2, 3 point. Now, leaving from the origin is the 1, 2, 3 vector. So, what this constant vector field says is that from any point, I'm going to get a vector that looks like that. So I could go ahead and draw in copies that look exactly like this guy pretty much everywhere else. You know, if I wanted to start at any point, I'm basically drawing in this same exact stupid vector everywhere. Right, so constant vector fields, easy to draw, but kind of boring, right? Everything's headed the same exact way, okay? You know, maybe it could be pretty easy to see how this could demonstrate something like, you know, like currents or fluid flow or something. Everything's going the same way. Now, like I mentioned, you can't have computers do this kind of thing. I'll go ahead and pull up kind of a web browser here real quick. All I did was a Google image search for vector fields. You can see what kinds of, you know, stuff that we can get out of this, both two-dimensional vector fields and, you know, three-dimensional things like this guy over here. You get all sorts of crazy stuff, just depending on whatever function you end up throwing into one of these guys. This is why I suggested that usually, this guy over here, it's probably a lot easier, you know, for more complicated stuff, just make a computer sketch it for you. Okay, this by hand thing is to give us a feel for where these come from. More practically, we would probably have a computer sketch a lot of the more complicated things for us. But, at any rate, back to our examples, we have a feel for, you know, where physically these arrows are coming from, how to get them, you know, what they mean on the graph. What I want to talk about at this point are some specific kinds of vector fields. Namely, one thing that I can talk about is something we've actually seen before. Recall, a couple sections back, especially when we were talking about the directional derivative, we started talking about a function called the gradient. Now, if f of x or f of xy is a scalar function, we found the gradient of that thing by basically building a vector that contained all of the first partials of that function in listed order, right? So if you have f of xy, you need fx and then you need fy. We had a similar three-dimensional analog for this. The gradient of a function of three variables, f of x, y, z, that vector looked like fx, fy, and then an fz on the end. Okay, but here I'm mentioning just the 2D one. You'll notice, if I look very carefully at what we're doing with the gradient, in 2 dimensions, this is a function that takes 2-dimensional input, and it spits out 2-dimensional vector output. Now, per our definition that we gave earlier, that means that the gradient of f is actually a vector field. You know, we can go ahead and make a similar comment for the 3D version, so I will go ahead and make that note. You know, similar for my 3D function f. your three-dimensional version just takes a three-dimensional input and spits out a three-dimensional vector output. So that guy's also a vector field. These vector fields actually have a special name. We call any, gradient of a 2D or 3D a gradient field. Okay, and these guys are, similarly functions that can describe, those situations that we described earlier, where we might want to express lots of vector quantities simultaneously, like force fields or currents or flows or things like that. So I'll go ahead and give an example here. Let's see if we can find the gradient vector field of f of xy equals this root x squared plus y squared. And I'll go ahead and see if we can sketch the field. Okay, well, really what this is asking here is basically find the gradient. If I'm saying find the gradient vector field, it's a really fancy way to just say find the gradient. We're just emphasizing that that object we get back happens to be a vector field, right? So if I'm trying to find this gradient, recall, all you do to find the gradient is find all your partials and then throw them in a vector, right? So I'm taking my x partial, I'm taking my y partial, there's no other variables, that's it, we're done after two partials. So if I'm computing that here, my x partial will call for chain rule. My derivative of this guy is really the derivative of a sum to a half power. So my derivative of my outside function is a half x squared plus y squared to the negative 1/2. Chain rule says, since I'm deriving with respect to x, I have to take a derivative of the inside with respect to x. That means I'm throwing a 2x on here. Similar deal in my y component. This is going to look almost identical, except for when it comes to taking the derivative of the inside function, you'll notice that we're deriving with respect to y because we're taking a y partial this time. That means here I throw on a 2y. Now this looks hella cluttered, so I'm going to go ahead and clean it up a little bit since I asked for y'all to sketch this. I don't want to sketch it now. It looks like a hot mess. So let's go through and take some cancellations, shall we? There's all these 2's and halves in here that I can get rid of. There's the fact that I really usually don't like negative or fractional powers. If I clean this up, those negative 1/2 mean that I'm basically taking a square root in the denominator. So in the first component, I'll get an x with this square root in the denominator. And then over here, I will get a y, okay, similarly, with this square root in the denominator, right? So this is my gradient vector field, right? Here is my name of my function. Since it does have the special name for it, this is one of the rare few cases that we won't put a hat on top of it, okay? This is referring to a very specific function that has a relationship to little f. But this is my gradient vector field, right? Just take the gradient of f and then copy down whatever your x and y partials are. Now, as far as sketching this thing, what I am going to suggest for sketching is this. Think smarter, not harder. There's an observation that I'm going to make about this vector that's going to make it a whole lot easier to sketch. Okay, I'll scroll down and give myself a little bit of room here. This gradient function that I'm looking at, it looks a lot like I have this root in the denominator for both of those terms. It's almost like, if I treated this like a scalar that I could pull out, I would get something that looked a lot like this. Okay, 1 over root x squared plus y squared times this vector xy. And technically, per vector algebra, we are allowed to do things like scalar multiplication. This maybe isn't a scalar per se, but, algebraically, this is scalar multiplication, the operation of that. And what it really looks like I'm doing here with this 1 over root x squared plus y squared, well, that root x squared plus y squared is really just me taking a magnitude of the xy vector, right? So this looks like 1 over my magnitude of xy times xy. So, rather than sitting here and picking 50 billion points and trying to set up a table and figure out vectors and things like that, what I'm going to note is this. If I want to sketch a particular point, I'm plugging into my gradient some sort of xy coordinate. What's going to happen is this. At that point, I'll think about what happens if I draw the vector from the origin to that point. However, I don't just want to copy over that vector. I want to divide by its magnitude, so that just means that I'm making it a unit vector. To demonstrate, here's kind of what I'm doing. Right? I could pick some sort of point here. Let's say I pick this guy. Now, if I wanted to just draw the xy vector from that point, well, if this is my xy, this is the xy vector. Okay, I'll highlight this little stretch with a hat on it, in case that was hard to see before. But the way that we draw vector fields is we draw vectors emanating from the given point. So I would basically want to pick up this guy, plop it down so that it starts at that point and then heads off in the same direction. But what our function does is it scales it to make it a unit vector. So what I'm going to go ahead and do is from this point, we'll pretend this is a unit, draw the unit vector in that direction. We can do the same thing elsewhere, like here. If I have this point, you'll notice that if I wanted to draw the vector from the origin to that point, but just shift it so that it started at that point, it might be here. But again, I want to scale this so that it's a unit vector. So we'll shorten that. Okay, we'll start with this guy and we'll just make it be a unit vector. Really the way to think about this is, since we're always picking up those vectors and shifting them to start at the point that we're working at, what we're really doing is at every single point that we want to draw one of these vectors, you are basically heading away from the origin, right? Every single one of these is going to head away from the origin, but it's all going to be the same exact length. Alright, so I'll go ahead and note that all my vectors point away from 0, 0, and have length 1. Okay? So, we'll basically get a bunch of these guys just emanating from the origin in this burst that goes outward. Pretty much the only place that we're not going to get a vector is 0, because if you divide by the magnitude of that guy, it's undefined. Okay. Now, question, now that we've kind of sketched that guy, how do a function and its gradient field relate? I'll go ahead and continue the example that we just did. Now, in that last example, in case you'd forgotten what function that we started with, we were working with root x squared plus y squared, and then I asked you guys to take a gradient of it and then sketch that gradient. Well, some comments. When we graph this thing, what object? Okay, if I graph the original scalar function, we graph that guy, what does it get? Well, this is one of the surfaces that I didn't touch on too much when we covered our surfaces section, but this, if you think of z equals, x squared plus y squared, if you squared both sides, that's your standard form for a cone. The square root here, in solving for z squared equals x squared plus y squared, if you solve that for z, that's going to give you the top half of a cone, meaning, We don't get the whole hourglass shape. We just get the thing that lies above the XY plane here. So this guy, if that actually connected to the appropriate spot, this is roughly the cone that we're looking at, okay, in my R3 space here. Get a cone whose tip lies at the origin. If you weren't certain that this was a cone, or if you weren't certain which direction that this guy, opened in, what you could consider was maybe think about what happens when you get a contour plot of this, right? Remember, for contour plots, you go setting your function equal to assorted constants to get level curves, and then you plot all the level curves on a graph. Well, here, what was my function? Looked like root x squared plus y squared. This is supposed to equal k. Well, if I go solving this for a more standard form, pretty much all of your level curves for this surface, they're all circles when we plot them in R2. Okay, so this thing is meant to be plotted in R2. Our level curves all look like concentric circles, and we'll pretend that last object is a circle and it's not super crooked. But this represents my curves of constant height on my surface, right? If I went back to my previous slide to kind of draw analogs of this, my curves of constant height on this surface, okay, if I wanted to draw them all the way around, that's corresponding to my contour plot right here. Now, a comment that I'll go ahead and make, if I wanted to recall what that vector field for my gradient of f looked like, well, we said that was full of all of those unit length vectors that just head away from the origin. Now, let's think about what happens if I were to overlay this thing on these graphs. I'll go ahead and do kind of a middle one here. I have all these contour plots, and then I have all of these vectors, and what I can notice happens, if I look very, very closely at any given location, I'll go ahead and scroll down here. This emphasizes one of the points that I mentioned to you guys about my gradient, right? So we could go ahead and recall my gradient points in my direction of steepest increase, right? And then this is also going to be perpendicular, or rather, if we wanted to use the more Calc 3 kind of word here, orthogonal to my level curves. Okay, so a couple ways we can analyze that. One, I tried as best as possible to try and make these vectors, my vector field, perpendicular or orthogonal to my contours and my contour plot. Another way to view this is we said that all of my vectors in my vector field basically pointed straight away from the origin. We are heading away from the origin at every single freaking point. Well, let's think about that in context of our surface. What is your direction of steepest increase if you are stuck on the inside surface of this cone? The fastest way to go up is to head away from the origin. So that's why your vector field is going to point outward, okay? So I'll go ahead and make some other comments about these gradient fields before I dip out here. A few closing comments that I wanted to make. That gradient vector field that we talked about before, we have a way to talk about vector fields that come from scalar functions because you took a gradient. Well, what if I'm just looking at a vector field and I want to know if it was a gradient? Well, we do have words for that. A vector field, if I'm starting with the vector field rather than the scalar function, a vector field is called conservative if it's the gradient of some scalar function. Okay, so if we're starting with this guy and you took a gradient to get there, we'll call that vector field conservative. And another comment, if you're trying to work backwards to figure out what the heck that function was in the first place, well, that original scalar function is called the potential function for your capital F hat. So for example here, we've worked at this function the past couple examples. If that is my capital F function, well, then what this is saying is that this capital F is conservative. It is the gradient of some scalar function. Specifically, it has a potential function given by that cone surface we talked about. F of xy was root x squared plus y squared. This is the function that you take a gradient of to get this function back, right? This vector field function. Okay, so that guy's conservative. Other things that we can go ahead and do, here we know that that one's conservative. We've seen this example in and out for most of this lesson. What if I gave you guys something else to start with from scratch, right? What if I give you this F? Is this guy conservative? Well, the question that I'm trying to ask is, does F look like basically fx, fy, and since we're in 3 coordinates here, fz for some function f of x, y, z. Right? Basically, does it look like gradient of f? Right? Well, let's see if we can verify this. Let's check. If so, let's go ahead and try to work towards this assumption. If so, I should expect that my antiderivative of fx with respect to x, this guy should look like my f function. Okay, you take an x partial to get there, you antiderive with respect to x to try and get back. Now maybe you might get some sort of weird constant of integration, but we'll try and see if we can deal with that. Similar idea here. We would expect to take a partial integral with respect to y of our middle term. Okay, we should expect that to give us f, and we should expect something similar with my z term to give us f. Okay, so let's see if we can find such a f, or do we maybe try taking all of these antiderivatives and we just get totally different junk back here and this is impossible. Okay, let's check this. Right, so I will take my antiderivative of that first function, 2xy squared. We'll do this with respect to x, and we'll see what this gets us. I'll do the same thing for my middle with respect to y, and I will do the same with that last function, that 0, with respect to z. Okay, so comment, if I antiderive this with respect to x, it looks like x squared times y squared, because the y squared is just a constant coefficient, and I'll go ahead and note, because we're being super careful here, there were no bounds on this. This is indefinite. If this is single variable calculus, we would get a constant of integration, but we have to be careful. This is a constant of integration as far as x is concerned. That means my constant is really a function of some sort of y and z. I'll call this C1. We'll name this like it's a constant function. Okay, there's some sort of y, z's maybe hidden in here. Similar deal over here. If I antiderive with respect to y, this is going to look like x squared y squared, and this time I will get some sort of a constant function that is in terms of probably x and z. Over here for this last guy, usually we don't take an antiderivative of 0, but let's think about this. What do you have to, derive to get 0? A constant. But we're talking about in terms of z here. So what's a constant in terms of z? Well, basically anything that's going to look like it's written in terms of x and y. So I'm going to get these three awkward constant functions here. The question that I'm going to ask myself is, can I reconcile this into a single function f? Well, comment that I'm going to go ahead and make. This guy right here looks like those might all be the same thing, right? I've got an x squared y squared that appears in both of these. That's pretty encouraging that we can pull an f out of this. And then I have this ambiguous, like, arbitrary function of x and y. Okay, whatever, sure. Let's C3 be this x squared y squared function. On the other hand, do I maybe have some sort of other function here on the end? Well, if I'm looking for an arbitrary function of y's or x's or z's, you'll notice, I can't have any additional y's, okay, because this doesn't really permit any additional y's. I can't have any additional x's because this guy doesn't really permit any additional x's. I can't really have any additional z's because, well, if I think about this, if I had z's in the first place, I should have found them using this antiderivative on my last row. So what this is probably going to suggest, at worst, if I have anything else that pops up as a result of, these constants of integration here, maybe, if I think about what happened in here and, what happened with part of my C3 function, maybe I might get some sort of plus C, like an actual legitimate constant on the end of this, and then that would be a totally functioning f, right? And we could double check this. Right? Let's see if we can try my f of x, y, z being just the function x squared, y squared, maybe with a legitimate constant c on the end. Now, let's think about what that gives you. If I take an x partial of this, I'm going to get 2xy squared and the c will drop off. That was what we started with in the first component. If I take a y partial of this, I will get 2x squared y in the first component, in the second component, and then the c will drop off. Okay, that was exactly what we got here. If I take a derivative of this guy with respect to z, everything drops off. That was exactly what we had in our last component. So here, we actually directly solved, and we found whatever our function was. So if I wanted to ask, consider this function is f conservative, well, did it look like a collection of partials for some function? Yes, right? Yes, it does. So since it does look like that collection of partials, okay, this is a potential function for that capital F. So since we've got a potential function, f is conservative. Okay? That'll be it for now. We'll look to start playing around with what integrals might look like in a space like this later on next week. So if anybody has any questions for me, please feel free to let me know. Either by email or you can stop by during office hours. Maybe bring stuff to class if you feel like you're a little lost on some stuff. Okay? Have a good rest of your weekend, guys.